Okay, Rams, this is your homework for Monday, March 2nd. If you're watching this, maybe you needed some help with it, or maybe you didn't. Maybe you just wanted to make for sure you had it right or check your work along the way. Either way, it's fine. Okay? So we're going to get started here. A caterer sets up a dining room for a reception with 6 chairs at each round table. Okay, so I could draw this if I wanted and say, like, here's a table with 6 chairs, 6 chairs. I could do a bunch of those, right? One table has 6 chairs, 3 tables have 18 chairs, 5 tables have 30 chairs. So which statement about this is true? Well, remember what we learned on Friday is that when you have a table here, your X and your Y are written like that. So X is always your independent and Y is your dependent variable. But you could always say the number of chairs that you need depends on the number of tables that you have. Okay, so we could go through and explain that here. But I know that chairs is dependent. So let's look at my answer choices. Chairs is dependent. Chairs dependent. That looks true to me. The number of tables is dependent. No, because that's on top, and that's always for my X, and that means it's independent. The number of chairs is independent. Nope. The number of guests at the reception is independent. Oh, nope. Actually, this has nothing to do with guests at all, does it? All right, so the one that is true is A. Okay. Next one here. At Bob's Burgers, each burger gets the same number of slices of tomatoes. The table below shows the number of slices used by Bob's Burgers in the last 5 days. Okay, what is the independent quantity? So right now we can look at the relationship between hamburgers and tomato slices, but that doesn't even matter. All we want to know is what's independent. So I know when my table is horizontal like this, that means across. The top is X and the bottom is Y. And X is always the independent variable and Y is the dependent variable. Okay, so let's just see which one is independent. Well, that's the top one here, the number of hamburgers. So that means the number of tomato slices we use depends on the number of hamburgers that we make. So independent is the top one, that's hamburgers. So the number of hamburgers. Okay, next. So these are a little bit smaller. Okay. JC has a collection of coins that has a maximum, oh, that's an important word there, of 30 coins. Her collection contains nickels and dimes. She has 12 dimes. Which inequality could be used to find the possible number of nickels in her coin collection? Well, inequality means I'm going to use a less than or greater than. Okay, so she has a coin collection, has a maximum of 30. So total, okay, so if it says maximum, it means no more than. So it means less than or equal to 30. My total is less than or equal to 30. It has nickels and dimes, so there are 12 dimes. So 12 dimes plus the number of nickels must be less than or equal to 30. So which one looks like that? Well, 12 plus n would either be A or B, but the maximum tells me that it's no more than 30, so it has to be less than or equal to, so it's A. Okay, next. David is buying a corsage for his date. The relationship between the cost of a corsage and the number of flowers is shown below. So 2 flowers cost $6, 3 flowers cost $9, 4 flowers cost $12, and so on. Which one is dependent? Well, remember, when we are looking at our tables, the first one we see is X and then Y. Just like the alphabet, the first one is X and then Y. X comes before Y, okay? X is always independent and Y is dependent. Okay, so which one is independent? Well, that is the number of flowers because that's what that column is. Okay, next we are at number 5 here. Okay, the graph shows the relationships based on the number of pints and the number of cups. And some of you may think, oh, I need to look at my formula sheet, my reference material, because it tells me that there are 2 cups and a pint. Well, that actually doesn't even matter here. We just want to know dependent, independent. Well, X is always independent, and my Y value is always dependent. So this says the number of cups depends on the number of pints. Okay? You could read it just like that. Find the one that's dependent and read that and say that one depends on this one. Number of cups depends on the number of pints. Oh, that sounds true. The number of pints depends on the number of cups. No, that's backwards. The number of pints is independent. There is no dependent quantity. Not exactly true. When we have a graph, there is one, okay? And there's not an independent, that's not true either. One of them does depend on the other, okay? All right, this one is not even from this unit. This is a topic that we have spiraled back in and pulled into review, okay? So look at this pattern here in your table. Which percent is equivalent to 5/4? Well, if 1/4 is 25%, 2/4 is 50%, 3/4 would be 75. What would 4/4 be? And then I would have 5/4. So 25, 50, 75, 100%. 4/4 is 1 whole, which is 100%. Now 5/4, that is 1 and 1/4. That's 1/4 bigger than the one before it. So each of these are 1/4 bigger. So I'm going to add 25%. So this is 125%. And you may say, wait. 100% means a whole. Yes, it does. But 5/4 is greater than 1 whole. So that's why your percent can go above 100, okay? All right. This one is about the reasonableness in multiplication. Okay, which of these statements is true? All right, so this goes back to those rules saying when I multiply by a number that is greater than 1 whole, my answer gets larger than the number I started with. If I multiply by a number less than 1 whole, my answer is smaller. And when one number is greater than 1 whole and one number is less than 1 whole, the answer is in between them, okay? Now, this one's a tricky one because you see 5/3, but that is greater than 1 whole. It's improper. So this is 54, it's a number, times a number greater than 1 whole, it's not going to get smaller. That's not going to get smaller, it should be greater than 54, okay? Again, the same thing right here. 3/2 is improper. This is greater than 1 whole. So if I take the number 28 and I multiply by something greater than 1 whole, my answer should be greater than 28. Okay, right over here, 49 times 3/7. Okay, 3/7 is less than 1 whole, so my answer should be smaller than 49. My answer is going to get smaller because it's like saying I'm taking a part of 49. So it's less than 49, okay? And this one, it's 140 times 2/5. So that's a number less than 1 whole, so my answer will get smaller, so it should be less than 140. Okay, 52% of the students wore jeans to school on Friday. Which statement would be an acceptable estimate of the fraction of students who wore jeans? Well, 52% is close to 50%. That means about. Okay, and 50% is 50 out of 100. And when I divide and simplify that, I'm going to get 1/2. It's about 1/2. Okay, next. Marty's dog eats 5 pounds of dog food every 4 days. What is the rate that this dog eats his food in pounds per day? So I'm going to put pounds and days. This is the abbreviation for pounds. It's LB. So it eats 5 pounds in 4 days. We want to know pounds per 1 day. Now, one thing you can notice here is that the pounds is a little bit bigger than the number of days. A little bit bigger. So this number here is going to have to be a little bit bigger than 1. Okay, so that means I can rule out this one because it's less than 1 whole. And I can rule out this one because it's less than 1 whole. Now, I could do the calculations here. But let's look at this one here. Look at 2. If I put a 2 here, it would mean that the number on top is twice as much as the number on bottom. I'll use a pencil so that I can erase it, okay? If I put a 2 here, that would mean this number is twice as big as that one, which would be okay as long as this number is twice as big as the 4, and it's not. So it cannot be a 2. Now, you could cross multiply and divide. 5 times 1 is 5, divided by 4. 4 times 1 is 4, and I subtract. And we have decimals here, so let's look at decimals. 4 times 2 is 8, and I subtract and get a 2, and I bring down my 0. 4 times 5 is 20. Now be careful, I'm noticing a lot of students adding in extra zeros up here where they're not needed. When you add a 0, it goes underneath your division sign here, underneath your little house. Okay? All right. Oh, goodness. Sorry, y'all, that was the guinea pigs over there making noise. All right, look at the distance covered and the number of hours required shown below. Okay, which of these represent a rate of 50 miles per hour? That means 50 miles in 1 hour. So I could say miles and hours, and I could simplify it. 150 miles in 3 hours. Is that going to be 50 miles in 1 hour? Okay, we could do this 3 times if we wanted. 500 miles in 10 hours. Is that 50 over 1? And the last one would be miles and hours. 600 miles in 12 hours. Is that the same as 50 to 1? Okay, a couple of things we can do. This one I could actually simplify. I could say, well, I'm dividing by 3. So divide by 3. Divide by 3. Is that going to be the same? If I divide both the top and the bottom by the same thing, do I get this ratio? 150 divided by 3. Yes. So that one's a good one. Okay. So this one here, I want to know, is this the same? Well, 500 divided by 10 is 50. So 10 divided by 10 is 1. So that one is good. Okay, well, do y'all know how many times 50 goes into 600? Well, 50 goes into 100 2 times, and it's 600, so it is 12 times. We would divide by 12 and divide by 12, and it is correct. Now, one other thing you could do, you could use the cross products, which some of you called from elementary the butterfly method. I don't like the name of it, but the process here, it's called cross products. You multiply the two that are diagonal to see if they're the same. And all of these are equivalent.